thank you all for coming here. You guys have a very nice big setup here. With all this. I'm surprised how well organized this is. We should probably get some tips from you how to organize our stuff at JPL. You're not as well organized. So I'll be talking about two different things today. First of all, I'll talk about this mission concept which me and some colleagues at JPL have been working for the past few years. We're trying to see how do we go from a point what we have right now on exoplanets to an actual full image of an exoplanet. Figuring out if you can see, like when you see Earth from far away from the moon, can we get that kind of resolution on an exoplanet? It seems very challenging if you want to just do it from the space. You need like a huge telescope, like multi-100 kilometers long telescope. There's no way anybody would fund that. But interestingly, we have our sun, which is a huge gravitational lens. So we just have to figure out how we use it properly. And that's where, so when I joined JPL 5 years ago, that was one of the first tasks I was given. And they were like, oh yeah, this is a blue sky study. Can you go and figure this out? So me and a scientist, Slava Turisha, he's been at JPL for more than 20 years now. He figured out a way to use the telescope from a science perspective and get an image. And then he asked me, how would we engineer this whole mission? So that's how we started on this concept. And we have been working on this for the past 2 years. We had multiple meetings at various workshops. And now we also talked with congressmen on that, and they are really excited. They want to see this going once we have enough people in Congress interested in this. So right now this is still a concept, but it doesn't take much time when there's enough people, enough inertia behind the mission concept to become a mission. And that's how the Europa mission came into the picture after like 10 years of being built. So this is fairly new. But this is pretty exciting. We're also getting some coverage these days. So let me start on introducing to you the whole motivation behind this. The whole motivation is, are we alone, right? That's where everything comes back to. So that was my motivation when I heard, like, oh, are we alone? And this is our Milky Way galaxy, and you guys probably know about this. And this is, and so I'm just preaching the choir here. But this guy really wants to be found, I think. And so we are trying really hard to figure out ways to get a better understanding on how to image exoplanets. NASA has been investing a lot of money into various telescopes in space, from Hubble to Spitzer to Kepler, TESS, JWST, which is upcoming hopefully soon, though it's delayed constantly because of technical challenges. But there have been multiple telescopes in space which have been looking over and trying to figure out exoplanets. And interestingly, that has sparked a new era of exoplanet discovery. The amount of exoplanets which have been discovered in the past few years is exponentially increasing. And that is because we have improved our methods to that tipping point, that now we can actually see them or get a signature on them, get a spectra, a very faint spectra, but at least something. So we know they're an exoplanet, we know it can be in the habitable zone. So that is very tantalizing. And all of that is actually being accelerated more and more every day. Like we have 3 more missions launching this year, which will start looking for more exoplanets. Then there is JWST, which will look for atmosphere on an exoplanet. And there might be like a day coming soon when we actually find an exoplanet which is very similar to Earth, based on the spectra. And what's next? We don't know. So that's what this mission is trying to cover, the gap. That huge gap between, oh yeah, we found something cool. What should we do now about it? Because there is no warp drive. We don't have warp drive to go there. So what's the next best thing we can do with the current technology and within the laws of physics? The 3 current methods we are using to detect exoplanets can be broadly divided into these 3 parts. The first one is the direct imaging approach. You just see an exoplanet with a chronograph and you see a small dot here, which is actually an exoplanet in a galaxy millions of light years away. Millions of light years away actually. And then there is another approach which is based on astrometry, which tries to understand the position of the star itself and how it's changing. Using that, you can figure out the orbit of the small planet around it and how far is it. And the third and the most recent one, which we have been using a lot, is the transit method. You see the exoplanet go in front of the star. The light of the star dims very slightly, but having an instrument which are cold enough in space can detect that dimming. And this is an actual spectra of one of the exoplanet detection we got. And this difference is on the order of gigabytes of nanometers, but you can still detect it now. And that's how you can see there's an exoplanet going. And you can actually get a lot of information on its basic composition of the atmosphere, how big is it, how far is it tidally locked or not. So I think, and a lot of people who I work with think this day is coming soon. Very soon we might get news on the Guardian or something that Earth 2.0 is discovered. We know there's an exoplanet which probably is in the habitable zone. It looks very similar to Earth. We're getting some good signatures from it. What is the next thing? And this is something the public will ask. NASA and also other space agencies. What is the next thing you have to do? And certainly we don't have warp drive anytime soon, hopefully. I mean, if there's one, that would be awesome. But there's nothing in works right now. So and that was a task we were tasked with. What to do next? How do we go from here to here? How do we convert that dot into an image like this? And initially we looked at possibilities of using huge telescopes, multiple small spacecrafts, combining to a single telescope. Everything resulted in a cost of at least $500 billion. So it was clearly not possible. That is a huge amount of money. NASA's budget is like $19 billion total. And astronomy gets like 10 to 20% of it. So there is not enough money to do what we wanted to do. But interestingly, there exists this nature's gift to us, which we have overlooked for now. And that gift is the solar gravity lens. And I'll talk about what it is. But the thing is, now that we have the Voyager spacecraft, which is already escaping our interstellar medium and going into real interstellar space, and with all these discoveries from Kepler and other spacecrafts on the exoplanets, we have what you can say, the field is coming close to that tipping point where an idea of getting a full image of an exoplanet becomes viable. And it seems like the logical next step from now. And that's where the solar gravity lens comes in. And when I heard first on this concept, Slava came to me and was like, hey, let's do a solar gravity lens mission. And I was very confused. I had no idea what that means. I was like, what do you mean solar gravity lens? And he was like, oh, good, you're confused. Let me explain to you. So that's what I'll try to do today. I'm trying to steal some of his thunder here. So it is a nature's gift. Sun is a gift for us. So what happens is, if you go to 550 AU from the sun, the Einstein ring, which forms around the sun because of laws of relativity, can be used to actually image an exoplanet which is millions of light years behind the sun. And there is a video which I will go over at the end of the presentation which will explain it to you very nicely. And there's somebody who actually makes me did it, so it's much better than I am. But the way it works is, imagine an exoplanet far away on this side, and the light is coming parallel, and when the light gets close to the sun, it starts getting bent. And the first point at which the closest light, just on the perifocal on the sun, meets is 550 AU. That's 550 astronomical units from the sun. 1 astronomical unit is from the distance between the Earth and the sun. So it's 500 times further away from the Earth to the sun. And if you can put in a small telescope there, you can image an exoplanet with a resolution of 1 million over a current small telescope. So it's a huge magnification factor with a very huge signal to noise ratio. But the challenge is now, how do we even get there? That's too far. How do we achieve? And that's not the point. We want to put a telescope beyond this, because that's how we actually get the full spectra and the full resolution of the exoplanet. So we started a new workshop, and the workshop lasted for 4 days, and out came this mission concept which I'll be talking about right now. But this basically gives you an overview of the whole distance from the sun all the way to Alpha Centauri. We just use that as a proxy. And this is in log scale, so you see all the planets, and they are in right scale but in log scale. This is where the Voyager spacecrafts are, the 2 blue dots, Voyager 2 and Voyager 1. And this is the 550 AU mark, where we want to reach to start using the sun as a lens. And the funny part is, if you reach that point quickly enough, you're going so fast, there's no way you will slow down. So what you do is, you just keep on going in a straight line. And this point doesn't become a point anymore, it's a line. So even though we say the solar gravity lens point, it should be called a solar gravity lens line. And the line is basically mapped, as you will see in the video, depending on where the light is coming from, near the sun. And And there's a very, very clear picture, clear version of this picture at very high resolution available on various websites. And if you guys want it, I'll send it to you with very high resolution. It's not even very cool to play here, but you can make it into a huge poster. And we did it in some of our outreach events. So we defined a mission to make this mission happen. We said we want to reach 550 AU, which is the distance where we want to start using the sun as a lens in less than 35 years from now. So imagine this, Voyager took 40 years to reach 100 AU. So we want to travel way faster than Voyager. And Voyager spacecraft took advantage of this planetary alignment, which only occurs every 300 years. So there's no planetary alignment for us to take use of. So we had to come up with a new way of doing this, and that is one of the tasks I was given when I joined JPL under probation. They're like, oh, you have 8 months, do something good, otherwise we'll throw you out. so I had to work out a way to do this, make this happen. And they also wanted to reach a hyperbelt object on the way out. They're like, oh, we're going there, why not we just visit one in less than 10 years? So what that turned out to was, the Voyagers are currently traveling at 3.5 AU per year in terms of their escape velocity. We want to go significantly faster, on the order of 14 to 20 AU per year. And it's exponentially hard to add 1 AU per year over each one before. So it becomes really hard to speed up because the rocket equation hurts you really bad. It's an exponential equation. So every AU per year you have to add 70% of all the previous fuel to increase that. So it becomes harder and harder, and suddenly you reach a point that your rocket is, your spacecraft is so big, there is no way a rocket can launch it. So we need to come up with a different way of making that mission happen. Before I go into the mission concept, let me explain you just small basics on how orbits work. So when, I'm sure you guys know all of this, but just to give you a very high level idea, an elliptical orbit is a simple orbit in which the body is getting faster as you get closer to the primary, and it gets slower as you get further away. So, and you can go from an elliptical orbit to a circular orbit, where it becomes equal in velocity all over the place, or you can go to a parabolic or a hyperbolic orbit. And when you're in a hyperbolic orbit, you are escaping that gravitational moment. So we want to achieve a hyperbolic orbit with respect to the sun. That was the aim. So the idea we came up with was, we will launch from the Earth, we will go close to Jupiter. And Jupiter is this big, massive planet in our solar system which can throw us back to the sun. Once we get close to the sun, we use the sun's gravity well to accelerate us at very high speeds. So we get really close to the sun, like 4 solar radii or 5 solar radii. And Mercury is like 100,000 solar radii, and it's already baking. So we get 4 to 5 solar radii close to the sun, then we use the heat to heat up hydrogen, which we carry, and we push the hydrogen at very high velocities from a huge nozzle, and that imparts a big change in velocity, very close to the sun. And what happens is, if you have a big delta V, we call it delta V is change in velocity, V stands for velocity. If you have a big delta V in a huge gravity well, the amplification factor on the delta V is on the order of 100. So if you do a delta V of 5 kilometers per second, you end up changing your spacecraft velocity by a factor of 1,000. So, and that is possible only when the gravity is huge. So it's something called an Oberth effect. You can Wikipedia it, it's on Wikipedia. It's a guy, Henry Oberth, he came up with this mathematical idea, and we have used it to slow down our spacecrafts. So whenever we do orbit insertions at Jupiter or Saturn, Mars, we come close to the planet and then we burn and slow down because it's way more effective. So we are trying to use the same concept but in the opposite way, close to the sun. So we get really close to the sun, we do a fairly large maneuver on the spacecraft, and we shoot out like bat in hell. And I'll show you an animation of an actual trajectory which I designed, which shows that happen. And on the left plot here, you will see the velocity change in the spacecraft. This is just a view from the top, and this is the view directly looking nadir down on the sun. And it's not that clear, I apologize for that. But you will see, oh, this is very bad. So you will see, I don't know if you see it, but this small dot is actually the spacecraft. This is flying by the Earth. So we do an Earth flyby because we don't have enough energy. The rocket we are launching on is the SLS, which is coming up, but we still don't have enough energy. It will go out to Jupiter, to Mars, it will come back, do another flyby of the Earth. Then it will go out again, and then it will do a flyby of Jupiter, and then it will come very close to the sun. And I apologize again for the resolution. I think it's the projector and the laptop not in sync. but you can see the spacecraft going out and you can see the velocity is changing. And you will see the velocity getting really fast when it comes very close to the sun, then it slow down again because the sun is pulling back. But even though it's pulling back, it doesn't have enough pull that it will escape the solar system at very high velocities. So after escaping from the sun, it reaches Saturn in 6 months. And generally it takes 10 years for us to reach Saturn. Like the Cassini spacecraft took 10 years, but this will reach in 6 months. So this is going really fast once it does that. So now it's coming back once more to the Earth, and then it will have enough push from the Earth to go all the way to Jupiter. And then Jupiter will throw it back to the sun for that one final huge maneuver, which you will see here as a huge spike. So, sorry, you're staying a while. It's pretty, in reality it will be much slower. It will take like 4 years for this whole dance to finish. So, in 4 years it will finally reach Jupiter. And we have to do all this dance because our rockets are not big enough yet. We can't throw something directly at Jupiter. We could, then we will not be able to put all that fuel we need to come close to the sun. So there's a trade we do, how much fuel you can put, how much faster you can throw it in space. So now see it goes to Jupiter and suddenly it just starts coming back. Because what Jupiter did was Jupiter basically changed your velocity in the negative direction and threw you back to the sun. And just coming close to the sun by itself is very hard because you need to cancel all that velocity of the Earth's orbit. But Jupiter can do it. But see how velocity is now increasing exponentially. You will see an exponential increase in velocity as it comes close to the sun. And just because sun is pulling, you see how it's going up, and then suddenly it dropped, and now it's like going out like hell. So we did a small maneuver here, and now it's like reaching from sun to Saturn in less than 6 months, and it's achieving a velocity of almost 18 to 20 km per year, which is hundreds of kilometers per hour. Like it's way faster than Voyager. And there were challenges of like how would we actually track this object? This is going too fast. This is faster than comets. So, but those are issues which we can tackle down the line. Right now the idea was just to understand if this is physically possible, and it turns out it is. And it requires this kind of mission idea that we launch on this new rocket which is coming up from NASA. We can also launch on a SpaceX one, the new Falcon Heavy. We can. It will just take a little bit more time to reach Jupiter, but we can do that. And then you will design the spacecraft so that it has these 3 components. This is the big solar telescope. On the front side, you have a huge telescope, or 1 meter telescope. And then you have all of this shenanigan you're seeing here. This is the heat shield, the front plate, the side plate. They basically protect you from the sun as you get within 4 solar radii. And this huge thing in the back is just a rocket. It's a big rocket motor pumping hydrogen out at very high velocities. And the hydrogen is getting heated up because you're getting close to the sun. So it's acting like a heat exchanger when you're coming close to the sun. So all of that was fun to work on, and the launch mass comes out to be like 11 tons if we do all the math. And out of that, 9 tons is just fuel, which is hydrogen. And this can scale up. So you can scale this idea up. If you have a bigger telescope, you can just get a bigger launch vehicle and a bigger rocket, and the idea still works. The concept still works. And this is how it looks like when you come close to the sun. It takes like 10 days from Mercury to the closest point of the sun because it's going so quickly, as you saw. And then when you come very close to the sun, you will turn to the sun, you will turn sideways, you will fire for like 5 minutes. That's all you need to fire for. You burn all the 9 tons of hydrogen in 5 minutes, and then you're out. So it's a very quick process, and the heat you accumulate is not much actually. It's surprisingly low. It's much lesser than entering into and landing at Mars. But the problem is the total heat flux over the whole mission timeline from here to here. So you have a different kind of heat shield design which you have to move for this. So the notional timeline which we were looking at is like, we really wanted to launch in mid-2020s. So we have started pushing this concept now up the chain to higher management, asking them, hey guys, can you do this, can you do that? And they are like, oh, we'll try. But there's no guarantee yet. So, but if we do get the money, we might have an SGL telescope in place by 2050s or 2040s, which will be a completely revolutionary technology or revolutionary asset, which we can ever add from a humanities perspective. And I will give you a much better idea of this mission. We actually hired an actual producer who made a very, very nice video and much better commentary than I could ever do. So I'll go over that video.
Exoplanets. They're just like regular planets but found in other planetary systems besides our own. So far, over 3,600 discoveries have been confirmed since 1992. These fuzzy dots are a few examples of the best direct images that we've got, and these are all gas giants like Jupiter. What we don't have is a really good image of an Earth-like exoplanet. It may actually be possible to get an image like this, but how we could do it may surprise you. We could use the sun as a lens. The sun is massive, to say the least, therefore so is its gravitational effect, which warps the very fabric of space itself. When incoming light from a hypothetical exoplanet approaches the sun, its path is also warped. These curved light rays are brought into focus starting from about 550 astronomical units away from the sun. The effect of gravity on the deflection of light is inversely proportional to its distance from the center of the sun. Approaching light rays further from the sun are not curved as much as light rays closer to it, so they come into focus past 550 AU, which results in a focus line rather than a single focus point. This is the solar gravitational lens. If we take a 1 meter telescope, place it at 650 AU away on the focus line, targeting an exoplanet 100 light years away, how much magnification and resolving power do you think it will have? From a fuzzy dot to a slightly larger fuzzy dot? Not even close. It could resolve details at the scale of 10 kilometers squared. That's like resolving the width of a single human hair on the moon from Earth, or an equivalent resolution like this image of Earth. If instead you targeted the closest exoplanet to us, Proxima b, at about 4¼ light years away, the resolution would be even greater, in the hundreds of meter scale. But there are not as many planetary systems to choose from right next door to us, relatively speaking. The sun, obviously, does not function exactly like a conventional lens. The sun's gravitational force warps the incoming light in addition to focusing it, resulting in a ring shape around the sun called an Einstein ring. Correcting this is a lot more work than a deep warping filter in Photoshop. Adding to the difficulty, we can't resolve the whole Einstein ring at once with just a 1 meter telescope either. If this same example exoplanet has an Earth-like diameter of around 12,700 kilometers, then that will result in an Einstein ring approximately 1.3 kilometers thick. This animation isn't to scale, as a ring will look more like this compared to the sun. But with those variables in mind, the area of the focus line that our telescope needs to cover would be a cylinder with a diameter of about 1.3 kilometers. You would need a telescope that's at least that size to resolve the entirety of the Einstein ring in one picture. That's 206 times larger than the primary mirror in the Hubble telescope. Fortunately, you don't need to resolve the whole ring in just one picture. Our 1 meter telescope can image an area on this example exoplanet 10 kilometers squared. So you can think of each picture it takes as a single pixel. You can still resolve the whole ring, you just need to assemble it pixel by pixel. The proposed goal is for a final image with 1000 by 1000 pixels, but that'll take some time as that adds up to a total of 1 million pictures. Before the imaging process can even begin, something has to be done about the sun. The telescope needs to face the sun to image the exoplanet, but unsurprisingly, its light would outshine the exoplanet. Since the Einstein ring is around and outside the sun, an internal coronagraph can be used which blocks the sun and the brightest part of the corona. There will still be some light from the corona mixed in, but not enough to completely overwhelm the exoplanet's light. For the coronagraph to be more effective, the telescope needs to be positioned further back on the focus line. That's why we can't place the telescope right at 550 AU, but still not too far back, as that could add years to the mission timeline. A good compromise would be between 650 to 800 AU. When the telescope is further from the sun, naturally it will appear smaller. The magnification of the exoplanet stays the same, but the Einstein ring is now at a greater distance from the sun's surface, so there's less corona light to contend with. But how far away are these distances really? An astronomical unit, or AU, is the distance from the Earth to the sun. At its greatest distance from the sun, Pluto is almost 50 AU away. Voyager 1 is currently traveling through interstellar space at 138 AU away from the sun, farther than any spacecraft has traveled. The telescope needs to be almost 5 times further than that. That distance, while considerable, may not be insurmountable. Here's just one possible hypothetical scenario. Using the currently in development SLS rocket as the launch vehicle, the spacecraft can get to Jupiter within 6 months. It can use a gravity assist at Jupiter, slingshotting the spacecraft towards the sun. As it falls into the sun's gravity well, within 5 to 7 solar radii, its velocity dramatically increases. When the spacecraft reaches maximum velocity through this maneuver, its rocket engines fire, adding to its acceleration and sending it on a trajectory to the focus line. Traveling between 17 to 22 AU per year, the spacecraft can get to 650 AU in about 30 years in the most optimistic scenario. But no spacecraft has approached this close to the Sun before, so a fairly robust solar heat shield will have to be designed and employed in order for the spacecraft to survive. Once there, the telescope has to move with the focus line and within it, as nothing in the universe is static. The exoplanet orbits its parent star while also rotating around its axis, if not tidally locked to its own star. While the trajectory design can account for much of this, a novel design for the spacecraft itself is still needed for it to move stably within the focus line. One idea is to build a spacecraft with the telescope on one end, tethered to a counterweight at the other end, using ion thrusters for propulsion at this point. The telescope can be pulled in or extended out along this tether to move within the focus line while maintaining a stabilized anchor position. This enables the telescope to gather a sufficient amount of images with less difficulty than keeping an untethered spacecraft stabilized. Using this method, it should take around 3 months to finish the task. But the challenges don't end there. Each image that the telescope takes is not a neat slice of the full ring. Instead, the telescope builds a rasterized image where each snapshot contributes more detail and magnification of a specific area on the exoplanet. These images end up overlapping each other, which can be considered a benefit as we won't need quite as many pictures for the desired resolution. Next, a deconvolution algorithm will be needed to fix the warped ring. While that may be a considerable challenge, we'll have the variables we need to correct it. The position of the spacecraft, brightness of each image at those positions, and the optical properties of the solar gravitational lens. If we are able to overcome all of these technical hurdles, we will finally have our first high-resolution image of an exoplanet. Using spectroscopy, we can analyze the light from the exoplanet in more detail than ever before. Gases absorb and emit their own distinct wavelengths of light. So when we analyze light from its atmosphere, we'll be able to accurately define its composition. Is the air breathable? Are there any telltale signs of life in the atmosphere, like methane, for example? Suppose there's actually intelligent life, and they too have electricity. Well, if it's nighttime and they turn on the lights, we'll see them. But there's more. Radio waves are just another wavelength of light. If ET is broadcasting, those radio transmissions will also be magnified, but not to the extent of visible light, as the radio spectrum is actually distorted by the interference of the sun's corona. While utilizing the solar gravitational lens is a daunting technical challenge, it still may be achievable in the near future. In fact, NASA's Innovative Advanced Concepts Program, or NIAC, recently accepted a proposal led by Dr. Slava Turyashev to further explore this very concept. This video is based largely on his paper and follow-up discussions with him. If you want to know more, you can find a link to his paper in the description below, as well as other relevant readings.
Alright, thank you very much for that one. So that's the whole solar gravity lens concept which we're working on. So now I'll give you a brief introduction on a very different topic, which is on the mission which pays my, which gets my paycheck, which is Psyche, which is the mission I've been working on for the past 3 years.